You may be surprised that gravity is actually the weakest of the four fundamental forces. It is the force that bonds planets and stars, and even galaxies together. It is also the force that keeps us away from falling off our planet. Now, how could it be the weakest? It is simply that on a tiny scale, gravity cannot overcome the three other fundamental forces. Today, we will learn the factors that affect the magnitude of gravitational force. This can be explained using Isaac Newton's universal law of gravitation. Newton describes gravity as a force that attracts everything in the universe that has mass to something that have mass too. And these things could be anything from tiny particles to galaxies. It is a universal law that treats everything the same way, but the strength of its attraction depends on the object's masses and the distance between them. Magnetism, for example, can make a piece of steel stick to it without falling to the floor as gravity would do. Circular magnetic lifters are used in industries to move anything from scrap to bulk of wires and metallic sheets. Gravity is the most familiar force to humans. We experience it every second in our everyday life. According to physicists, there are four fundamental forces that exist in the universe, and they are called the fundamental forces of nature. These forces drive the motion and behavior of everything we see around us. First fundamental force is gravitation, or simply gravity. It is the universal force of attraction acting between all matter. It is by far the weakest known force in nature and thus plays no role in determining the internal properties of everyday matter. On the other hand, through its long reach and universal action, it controls the trajectories of bodies in the solar system and elsewhere in the universe, and the structures and evolution of stars, galaxies, and the whole cosmos. Electromagnetism or electromagnetic force, some others call it Lorentz force, explains how both moving and stationary charged particles interact. It is called the electromagnetic force because it includes the formerly distinct electric force and the magnetic force. The strong force or strong nuclear interaction is the strongest of the four fundamental forces of nature. It binds the fundamental particles of matter together to form larger particles. It holds together the quarks that make up protons and neutrons, and part of the strong force also keeps the protons and neutrons of an atom's nucleus together. The last fundamental force is weak force or weak nuclear force. It is responsible for particle decay. This is the literal change of the one type of subatomic particle into another. So for example, a neutrino that strays close to a neutron can turn the neutron into a proton, while the neutrino becomes an electron. The weak force is critical for the nuclear fusion reactions that power the sun and produce the energy needed for most life forms here on Earth. There's a popular story that Newton was sitting under an apple tree. An apple fell on his head and he suddenly thought of the universal law of gravitation. As in all such legends, this is almost certainly not true in its details, but the story contains elements of what actually happened. Probably the more correct and better version of the story is that Isaac Newton, upon observing an apple fall from a tree, began to think along the following lines. The apple is accelerated since its velocity changes from zero as it is hanging on the tree and moves toward the ground. Thus, by Newton's second law, there must be a force that acts on the apple to cause the acceleration. Let's call this force gravity, and the associated acceleration as acceleration due to gravity. Then imagine the apple tree is twice as high. Again, we expect that the apple to be accelerated toward the ground. So this suggests that this force that we call gravity reaches to the top of the tallest apple tree. Now came Newton's truly brilliant assumptions. If the force of gravity reaches to the top of the highest tree, might it not reach even further? In particular, might it not reach all the way to the orbit of the moon? Then the orbit of the moon about the Earth could be a consequence of the gravitational force because the acceleration due to gravity could change the velocity of the moon and just such a way that it followed an orbit around the Earth. Newton knew that the force which caused the apple's acceleration must be dependent upon the mass of the apple. And since the force acting to cause the apple's downward acceleration also causes the Earth's upward acceleration, that force must also depend upon the mass of the Earth. Thereby, using those assumptions, Newton was able to organize his thoughts and develop come up with this equation. As we put it mathematically, he says that the force of gravity that the force of gravity is directly proportional to the mass of the two objects interacting, but is inversely proportional to the square of the distance between the two objects. Since we have here a proportionality symbol and we want to calculate it mathematically, we can change it with an equal sign, and we need to provide a proportionality constant. And we now have the basic equation for Newton's law of universal gravitation. That is, gravitational force is equal to G, that is the universal gravitation constant, multiplied by mass sub 1, mass sub 2, all over the distance between the two objects. In other books and even online, others might use just simple F and then capital G for the constant and then capital M for the mass of the first object and a small m for the second. And then instead of R, they use D, but we still square it. In summary, F is the force between the objects. G is the gravitational constant with the value of 6.674 times 10 raised to negative 11 Newton meter squared per kilogram squared. M sub 1 and M sub 2 are the masses of the first and second objects respectively, and R is the distance between the center of the objects. Though we use the second law to formulate the equation for for Newton's universal law of gravitation, we can confidently say that this is also an extension of Newton's third law. If we imagine his assumptions, if this is the Earth and we have the moon orbiting around it, he says that using Newton's third law, an object exerts a force on the other object while the second object exerts a force on the first object. That means that there is an action and reaction forces in between the interaction of the two objects here. So since we have Earth and the moon, so we say that the Earth exerts a force on the moon while the moon also exerts a force on the Earth upon a certain distance r. Using the third law, we say that the Earth exerts a force on the moon is equal to the force exerted by the moon on the Earth. Since they differ in direction, so we say that we still follow Newton's third law. Now, how did we come up with the value of G? So that was a century later that was discovered by Henry Cavendish. So the constant G is called the universal gravitational constant, and Cavendish determined it to be 6.67 times 10 raised to negative 11 Newton meter squared per kilogram squared. So he constructed a device similar to that shown in the figure, and in which small masses are suspended from a wire. Once in equilibrium, two fixed larger masses are placed symmetrically near the smaller ones. The gravitational attraction creates a twisting motion or a torsion in the supporting wire that can be measured. Thus, we have the value of G. He also found out that G applies to masses of any composition and that it is the same throughout the universe. then the value of g is an incredibly small number, and the force of gravity is very weak. We will not deal so much as to how it was computed, but he needed to use his knowledge of force, torque, static equilibrium, oscillations, torsion, and moment of inertia. More experiments were done to check his work, and they found out that Cavendish had a very high accuracy with only 1% margin of error. Now, if we'll try to trace the equation that he used for the value of g, he come up with the equation using his experiment as g is equal to 2 pi squared L theta r squared all over t squared m, where g is the universal gravitation constant, pi, which is equivalent to 3.14, then the length of the torsion bar that he used, then the angle the bar turns, that's theta, and then we have r, which is equivalent to the equilibrium point distance between the larger and the smaller masses, oscillation frequency, and the mass of the larger object. It is important for us to review the difference between mass and weight and the relationship of weight with gravitational force. As we know, mass is the measure of the amount of matter in an object, while weight corresponds to the amount of gravitational force pulling the object down. So since W is equal to Fg, we can rewrite the basic equation of the second law, that is F is equal to ma, into W is equal to mg, where m is the mass of the object and g is the acceleration due to gravity, that is 9.8 meters per second squared on Earth. So we come up with the relationship now that mass is directly proportional to the weight. So any increase in the mass will cause an increase in the weight of the object. In this example, we have a mass of 10 kilograms, and on weighing scale will give us 10 kilograms. Computing it using our equation from the second law, W is equal to mg, we come up with 98 newtons. But that will be a different case if we put the object on the surface of the moon, since the acceleration due to gravity on the moon will just be 1/6 that of the acceleration due to gravity on Earth. Thus, we will have an answer of only 16 newtons when assuming that we have a box on the surface of the moon. And that will be 0 if we put the box or suspend the box in outer space, not really close to any celestial body. Using also the equation, we can see how the mass affects the force of attraction between the objects. If you rewrite it, the force of gravity is directly proportional to the mass. So the greater the mass of the object, the greater the force of gravity that it has. So suppose we have two objects here interacting with one another with the following mass representations at a distance r. So we can have a value of just simply f. But how about if we double the mass of one of the objects, like this one? So we have the mass of the first object, and assuming that we have the same distance, this is mass number 2. So we double the mass of this object at same distance. So what will be the value of f? Since they are directly proportional, so we can get a value of 2f. So the force will also double. Doubling the masses of the two objects at same distance will give us a factor of 4 that will be quadruple. So the amount of force will increase by a factor of 4. In our last example, we have here a mass, regular mass similar to case number 1, and then same distance r, and we have the second object that is thrice the mass of the first object will have a force that is also thrice the amount from the original. How about the distance? As we recall, the force of gravity is inversely proportional to the square of the distance between the center of the two objects. So let us assume that we have mass 1 here interacting with another object with a similar mass. So if this is the distance, in case A, we just have a force F or amount of force F. But if we increase the distance, M, then we double the distance. So just estimate this one. So what will happen to the force? Or what will be the resulting force? Since we double the distance, and this is an inverse square proportionality, so that will decrease by a factor of 4. So that will become 1/4 F. So it will decrease by a factor of 4. When we decrease the distance between the two objects, eventually we expect that the force will increase. So this is assuming that this is 1/2 of the original distance that we have in case A. So we get an increase of 4F. So that will increase by a factor of 4. This one will decrease by a factor of 4 since we have an inverse square proportionality. So you can also have this case where we have an object that has twice the mass and then another object that has twice the mass, though you increase the force since you are increasing the mass, but you double the distance between them, you'll just get a value of F similar to case A. Let us check your understanding by answering this question. Number 1. Suppose that two objects attract each other with a force of 32 newtons. If the distance between the two objects is doubled, what is the new force of attraction between the two objects? Okay, time is up. So we have here a value of 32 newtons. So the value of gravitational force existing between the two objects is 32. And we want to suppose that the distance is doubled. So if you double this up, you increase, it will be a factor of 4. It will be a factor of 4. So what you need to do is just simply divide your given of 32 newtons by 4. So there will be a decrease by a factor of 4 and your answer will be 8 newtons. Second one, if you wanted to make a profit in buying gold bars by weight at one altitude and selling it at another altitude for the same price per weight, should you buy or sell at the higher altitude location? What kind of scale must you use for this work? Okay, time is up. So answer will be, so to profit, you need to buy at high altitude. and then you need to sell it at low altitude. So think of the explanation. So I'll leave it up to you. So usually I proceed on solving problems using Newton's law of gravitation. So these are some tips that we need to consider. So you may follow it when you are still practicing and knowing this law. But if you are used to it, we can directly compute it using our calculator. So to determine the motion caused by the gravitational force, follow these simple steps. Number one, identify the two masses, one or both, for which you wish to find the gravitational force. Two, draw a free body diagram sketching the force acting on each mass and indicating the distance between their centers of mass. And then we can already apply Newton's second law of motion, the equation that we had earlier, to each mass to determine how it will move. So let's try this one as our first example. So a 1 kilogram object is located at a distance of 6.4 times 10 raised to 6 meters from the center of a larger object whose mass is 6.0 times 10 raised to 24 kilograms. So we are asked to find for the magnitude of the gravitational force. So assuming that we have these two objects here on the right side, and then we assign mass sub 1 for 1 kilogram, and then for the bigger one or the heavier one as mass sub 2, and then we have the distance between the centers of the two objects as 6.4 times 10 raised to 6 meters. So let us write the given following GRESA for us to be organized in this example. So you have a given of mass sub 1 that is 1 kilogram, and then we have the distance between the two objects as 6.4 times 10 raised to 6 meters, and then we have the mass of the heavier object 6.0 times 10 raised to 24 kilograms. So we are required to look for the value of G, Fg, or the force of gravity. So just by using the equation that we have earlier, that is force of gravity is equal to the gravitational constant times mass sub 2 times mass sub 1 times mass sub 2 all over the square of the distance. We just need to substitute the values that we have there. So we write this one. So Fg is equal to 6.67 times 10 raised to negative 11 Newton meter squared kilogram squared multiplied by 1 kilogram, and then multiplied by the mass of the heavier object 6.0 times 10 raised to 24 kilograms all over the square of the distance. That is 6.4 times 10 raised to 6 squared. So let us compute for the numerator part first. So we'll have a value of about 40.02 times 10 raised to 13 all over the square, that is 40.96 times 10 raised to 12. To continue with our calculation, so we'll have an answer of 0.977 times 10 raised to 1. You just need to adjust the decimal point so that we can get a standard form of the number, that is 9.8 newtons. That will be the value of G in this case. Now, how did we cancel out? So you may do it on your paper, how to cancel out all the units so that we can get just the unit of Newton in the end of our calculation. Let's try another one. So we have two spherical objects that have equal masses and experience a gravitational force of 25 newtons. Their centers are 36 centimeters apart, and determine each of their masses. So in our figure, we have assigned, they have the same masses. So we have m sub 1 and m sub 2, and are separated by only 36 centimeters. So let us begin again with the given. So the given that we have in this problem is the force between the two objects, that is 25 newtons, and then we have r, the distance between them, that is 36 centimeters. So we convert it already into meters, that is 0.36 meters that we will use later to determine each of their masses. So we are required to look for the mass. Since they're just the same, so just put m as our required. Let's go through our equation and derive a simpler one to get what we need to calculate. So we have Fg is equal to G m1 m2 over r squared. Since m1 is equal to m2, so we can just square this one to simplify our equation. So we have Fg is equal to G m squared over r squared. Then we need to cross multiply. Fg r squared is equal to G m squared. So we're looking for the value of m. So divide both sides by G. To eliminate G on the right side, we'll have m squared is equal to Fg r squared over G. We need to eliminate the square, so we need to square root both sides. So we'll cancel this out, and we'll have this equation, the square root of f multiplied by r squared over G. So this will be the equation that we will use in this problem. Let's now substitute our given. So we have mass is equal to, so the value of F is 25 newtons times R, that's 0.36 meters squared, all over 6.67 times 10 raised to negative 11 Newton meter squared kilogram squared. Again, this is a constant. So it is for us to familiarize the numerical value of G. So it's the value of this 25 and 0.36 squared. Let's compute it. So we have 3.0625 all over 6.67 times 10 raised to negative 11. So I won't include the units anymore since we are canceling this out later. So we'll have an answer of 4 point square root of 4.56 times 10 raised to 10. So that is, you imagine that's times 10 raised to 0 plus minus negative 11. So 11 at the denominator will become positive sign. So having the square root of 4.56 times 10 raised to 10, we'll have an answer, final answer of 2.14 times 10 raised to 5 kilograms. So these are the masses of the objects, the two objects respectively. Let's have our third example. So we have a 55 kilogram man is located at a distance of 7.0 times 10 raised to 8 meters from the center of a larger object whose mass is 2.0 times 10 raised to 30 kilograms. What is the size of the force acting on the smaller object? What is the magnitude of the force acting on the larger object? What is the acceleration of the smaller object when it is released? And what is the acceleration of the larger object when it is released? So we need to look for four required variables. So let's draw our situation. So I will just assume that this mass is a planet. So you have a 2.0 times 10 raised to 30 kilogram. It refers to a planet. Then we have a man standing on the surface of that planet, which is 55 kilograms. So let's designate this one as M1. Then this one is M2. And then the radial distance from the object of the two objects from each other, we just consider this one, 7.0 times 10 times 10 raised to 8 meters. So this will be R. So hindi natin susulat yung given. We proceed with the required. Later na yung required. So our equation will be F G is equal to the gravitational constant M1, M2 all over R squared. So the first question is, what is the size of the force acting on the smaller object? So you just need to use this one. Substitute the value of G, that is 6.67 times 10 raised to negative 11 Newton meter squared, kilogram squared, multiplied by the mass of the first object, 55 kilograms, times 2.0 times 10 raised to 30 kilograms all over the distance of 7.0 times 10 raised to 8 meters squared. So we'll have, let's compute this, 6.67 times 10 raised to negative 11 multiplied by 55 and 2. So we get an answer of 733.7 times 10 raised to 19, and then the square of the distance is 4.9 times 10 raised to 17. Dividing it, we get an answer of 149.73 times 10 raised to 2. Raised to 2. So we can convert it into standard notation. Since just a small number, we'll have 14,973 newtons. Now, if we look at the units, so we'll have an end unit of newtons. Since we can cancel out this one, so we square the distance, then we have here at the denominator the meter squared from the constant, and then we have kilogram can be cancelled out from the given masses of the two objects. Since it is in the denominator, we can cancel this out. So this is our answer for letter A. How about for letter B? What is the magnitude of the force acting on the larger object? Again, following a third law. So the force on object 1 exerted by object 1 is also the same as the force exerted by object 2 on object 1. So our answer for B will also be 14,973 newtons. For letter C, hindi na siya kasya. That's a simple equation for letter C. We just need to use F is equal to ma for object 1 or for the smaller object. So the acceleration, we're looking for tangential acceleration of the object. So A is equal to F over m. So what is the force? 14,973 divided by the mass of the object, that is 55. We get an answer of 272 meters per second squared. How about for letter D? Okay, let's erase some parts. Okay. Go back with our pen. Okay, for D, the value of D, that is the acceleration of the larger object. We also use this equation. We'll have A2 is equal to F, the value of F that we have computed, then mass 2. So we have F, that is 14,973 all over mass of the object, that is 2 times 10 raised to 30 kilograms. Our answer will be 7.49 times 10 raised to negative 27 meters per second squared. As you see, the value of acceleration for a larger object is too small because it is still not really affected by the smaller object. So in this case, although they have the same force, but the effect will be different. The effect on the motion on the objects will be different. Let us have our last example. So we have a 1,500 kilogram satellite that was originally placed into an orbit of radius 24,000 kilometers in a period of 31 hours around an unknown planet. What is the mass of this planet in terms of the universal constant g, the radius r, and the period t? We're only to get the value of the mass. So we're looking for the mass of the unknown planet with the given data that we have. So do not be confused with the question. Those are the variables that we will use in this calculation. So imagine that this is the unknown planet, and then we have a satellite that is 1,500 kilograms, and from the center of the planet we have 24,000 kilometers, and it takes 31 hours for the satellite to take one complete revolution around the planet. Okay, let's have our given. So we have the mass of the planet, of the satellite, sorry, that is 1,000 kilograms. And then we have the distance between the two objects, that's 24,000 kilometers. So convert natin ito, that will become 24 million meters. And then we have a period of 31 hours. So we don't have any value for force. So we need to derive it. So we are to find for the mass of the planet. So how will we come up with that equation? So we need to remember that this law is related to other concepts, a concept extension of the second law. So since it's a planetary motion, we can use the equations for uniform circular motion. So let's write first our basic equation. F g is equal to g times multiplied by m sub 1, m sub 2, all over r squared. So we know that in a planetary motion or uniform circular motion, Fg is also equivalent to the centripetal force, that is ma. Since it is in a circular motion, so we derive an equation for ma, since a is equal to v squared over r. So inserting that equation here, we have Fc is equal to mv squared over r. Again, Fc is just the same with Fg. This force pulling the satellite towards in the orbit is the centripetal force and also the gravitational force. So Fc is equal to Fg. So we can equate it. You can equate this equation together with this one. So let's try it. So we have m v squared over r is equal to g m1 m2 all over r. So you do some cross multiplication. We have m v squared r is equal to g m1 m2 then r. This is r squared, sorry. So this is r squared. Now, we have the value of the masses. So mass 1 is actually the mass of the satellite. Then mass 2 is the mass of the planet. So this one that we are talking about in the where the centripetal forces is acted to is on satellite. Is acted on the satellite. So this one will become ms. So since we need the value of the mass of the planet, so we need to eliminate all the variables on the right side. So we'll have g, mass of the satellite. Then we have the r, or radius. So we can cancel this out. G, ms, m sub s, r. So this one will be cancelled out also. And then 1r will remain. So we will come up with an equation that is mp, the mass of the planet, is equal to v squared r over g. So we still don't have the variable t, so we will still continue with our derivation. Since v is equal to 2 pi r over t, so another variation of it, if you have frequency, is 2 pi rf in uniform circular motion. So we assume that the orbit is circular, okay? So we will insert this one to this formula. So we'll have mp is equal to 2 pi r over t times r all over g. So let's evaluate first this one. So that's v squared. So we have mp is equal to 4 pi squared r squared over t squared multiplied by r all over g. And then if we organize this equation on the right side, we'll come up with this equation. M sub P is equal to 4 pi squared R. So since R squared and R are both on the numerator side, the numerator part, so they will be R, or this will be R cubed. And then T2 will now go to the denominator side, T2 and G. So our equation will now be like this one. The mass of the planet is equal to 4 pi squared R cubed over GT squared. So we can now proceed with our calculation. So the mass of the planet is equal to 4 times 3.14. The square of 3.14 multiplied by the cube of the radius, that's 24 million meters, all over the value of G, 6.67 times 10 raised to negative 11. And then we have the period of 31 hours. So that will become 11,600 seconds. 1,600 seconds. Yeah, let's compute it first. Okay, for this one alone, we get an answer of 39.4384 multiplied by the cube of 24 million. Just using my calculator. We have 24 million. That will be 1.38 times 10 raised to 22 all over the value 6.67. So I'm just showing you the computation for each operation that we have in the equation. So I still put 6.67 times 10 raised to negative 11. And then the square of the period, which is equivalent to 1.35 times 10 raised to 8. So you now multiply these two on top. So we get a value of 1.44 times 10 raised to 23. This is 2 all over 9.0 times 10 raised to negative 3. So what will be the resulting mass of that planet? So we'll have an answer of 6.604 times 10 raised to 26. This is just the number. You get 6.04 times 10 raised to 25 kilograms. That will be the value of P. So let us see how did we cancel out our units. So there are no units for pi. We have the cube, m cube, and then we have the value Newton, meter squared, kilogram squared, and then we also have second squared here. So we need to evaluate Newton into kilogram meter per second squared. So by doing so, you can cancel out the time in seconds squared, and we have kilograms. We can cancel 1 since we have a reciprocal of this one, so that will not be a negative sign. So this one will be a reciprocal, so we'll have kilogram remaining for our unit. And then we have 1 meter here, a meter squared. We can cancel this out. We can get just 1 kilogram for our answer of 6.04 times 10 raised to 25 kilograms. And that's it. So in summary, what have we learned in this law? Number one, the force of gravity is very weak. Second, mass and weight are proportional to each other, with the acceleration due to gravity is the proportionality constant. The value of g is an incredibly small number, as suggested and proven by Henry Cavendish. Fourth, the factors that affect the magnitude of gravitational force are the mass of the objects and the distance between them, as seen in our equation. Fifth, the force of attraction between the two masses is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. That is a more comprehensive uh, detail of the fourth idea that we have. So we can uh, represent it by this equation: F gravity is equal to G multiplied by a capital M, small m, all over r squared. Or you may use the other one that I gave earlier. Lastly, knowledge of Newton's second law, uniform circular motion, rotational motion, and even Kepler's law are fundamental in solving problems in universal law of gravitation. So this one will be written on your paper. So at least one bond paper for each lecture. So we have 2 questions here. So you need to solve completely this word problem. The distance between Earth and Moon is 3.84 times 10 raised to 8 meters. What is the magnitude of gravitational force each exerts on the other? Known values are Earth's mass, 5.97 times 10 raised to 24 kilograms, and Moon's mass, that is 7.35 times 10 raised to 22 kilograms. So you may pause this part so that you can copy the equation on your the problem on your paper. The second one is an essay type question. You need to answer it in 3 to 5 sentences. Though the law of universal gravitation can explain many physical phenomena on Earth and space objects, can you cite 1 to 2 situations that violate this law or seem to follow the general theory of relativity? Why do they not strictly fall under UGF? If you have time to read additional reading, you will notice that Newtonian mechanics is not absolute true when we compare it or when we learn the both special and the general theory of relativity by Albert Einstein. So these are references. You may also watch other videos in YouTube. You may also read some text so that you can uh, learn more about this law. Thank you for watching and good day.